Welcome to lecture 17. Yesterday we were looking at some very simple method of analyzing flow nets or constructing flow nets, and we could build them for the following cases: what you can call confined flow, unconfined flow, and of course we also looked at how to transform flow through anisotropic media. We transform the coordinates, particularly the x coordinate, so that an anisotropic media becomes an equivalent one. X is equal to, what it means basically is confined flow means if you have a, let's say, stratum which is bound, and then we have the flow is confined between the top and bottom boundaries, and here is the net head difference between the upstream and the downstream side. Similarly, we can have a weir or a barrage. Let's say I'm having a weir here. We can also provide a sheet pile or a cutoff so that the length of the flow path increases, so which means that the flow will be now longer than what it would have been if there had been no sheet pile. So here again is the net head difference H. So this we call, these are all again, since the bottom is resting on an impervious shale or rock, whatever stratum, there can be no flow below the dam. So here are the, and then we try to draw the equipotential lines, something like, let's say, so that each of these figures we would like to keep as close as possible to a square. That is the beauty of flow nets. You can also build a similar one, a deep excavation. Here is a building that you want to construct. The groundwater level is high and you would like to keep the excavation dry. So then we provide the sheet piles, and then you will find that similar to the weir with a cutoff, you will find the flow lines would be something like this, and you can now draw the something like this, etc. So we can complete the whole flow net. If you can build the flow net properly, I would say the most important thing is a proper network or net. One, you have to have the equipotential lines should meet or perpendicular to the flow lines, and the size of the element, each element is approximately a square. When I said a square, I think you remember we said either the diagonal should be same or the midpoint length or distances should be the same. If you can construct such a good one, we have two important things you can make out from the flow net. One is the rate of discharge, which is very easy to calculate, is coefficient of permeability times the head drop, if I use small h here, and number of flow paths by number of head drops. You can see here we have, let's say, 1, 2, 3 maybe flow paths, and then head drops 1, 2, 3, 4, 5, 6, 7, 8, 9. So all that you have to do is from your flow net calculate how many flow paths are there and how many head drops are there. And this is a very simple number, coefficient of permeability times the net head loss will give you the discharge through the medium. The second class of problems we looked at are the unconfined flow, which is mostly through at the dams. We build to store water, which are a very common feature in all the places and one of the most busy activity of civil engineering. So here is a dam you are building and you want to store water here. Let's say the downstream water level is near the ground level, and to start with we say the dam is founded on an impervious stratum. So here the major problem would be to find out what is the topmost flow line. Let us say if I look at the water molecule here, how does it travel to reach the downstream side? For all I know, it may come and hit the downstream phase somewhere here. Obviously, it has to become tangential, and this line we call it as a phreatic line. You can say topmost flow line, and this is not known beforehand. We'll have to build it. The main characteristic of this is along the phreatic line, the pressure head is 0, or you can say H due to pressure head is 0. So the total head is equal to simply elevation head. So if I want the head at any point, this is simply equal to the height of the point from the datum. If I take another point here, this will be, say, Z1, and as you know that it goes down, the head decreases as you go to the downstream side. So what is necessary is to find out this length L, which we got from Dupuis assumption, which says the gradient is approximately equal to the slope of the line. So if I take the slope of this, for example, dz dx, and that is how you do that. And based on that, we have an expression which we gave yesterday. If you want, we'll again write it down. For flat slopes of the order of, let's say, if alpha is less than or equal to 30 degrees, Dupuis assumption is valid. L is equal to d by cos alpha minus square root of d square by cos square alpha minus h square sin square alpha, where h is the head difference and d is this distance from the toe of the dam, and this point is actually, if I call this distance as delta, this is 0.3 delta. So knowing the geometry of the problem, we know what is d, we know what is the head loss, and we can easily find out. Casagrande, another researcher, he found out that for alpha greater than 30 degrees, L is given by square root of d square plus h square minus d square minus h square cot square alpha. So it's a slight change difference, and you can easily calculate what would be the discharge. Once you get the whole analysis done, all you have to do is construct the top flow line. After that, I can simply draw the flow net again. Once you draw the phreatic line, the flow region is bounded. It becomes more or less confined. So we draw the flow net and then calculate discharge, etc. One point I would like you to realize here is that the water is entering onto the slope, and if you look at this soil, it is subjected to a phenomenon called piping. So let us see what is this piping phenomena. When the flow is coming out of the soil, flow from soil to atmosphere, the fine particles are carried away. Let us say we'll plot the grain size distribution here. I'm plotting diameter d and percentage finer. Let's say the particle size distribution is something like this, and here is our d10, 10%. Now usually the void size is approximately equal to d10 in terms of millimeters. Look at the particles. This size is approximately d10. If I have particles which are finer, whose size is less than d10, if the particle size is smaller than the void size, the particle will go along with the water. So what will happen is, through this, all the finer particles will go away, and now suddenly you will find that the grain size distribution has become coarser. So the fine particles are washed away or carried out, then the voids become larger. the permeability becomes larger, the flow increases, and continuously this material will fail, and you may find what you call a slumping and even failure. We have in the literature in our country too, if the downstream end where the top phreatic line comes and meets the surface, if it is not protected properly, there is going to be a piping phenomena. And if that happens, there could be failure and it's a disaster. So what can we do to prevent? If you go for a course on earth dam design, you will find it. One of the ways we do is pitching. I'll put in stone, pack it around so that this will come and large stone particles cannot be pushed away. So that one of the techniques is pitching. Another technique we use, which is actually more or less common, is to provide drains. We do not want the top flow line to go to the right downstream slope, so make sure it's within the embankment itself. So what we do here is provide what you call as a toe drain. So these are all gravel particles, so that when you have the top flow line will come, and this being a highly pervious material, water will have a tendency to get attracted, and so you provide, and the gravel size can be of the order of up to 300 mm. You can put large size gravel particles there. And another form of drain would be a blanket drain. This is again large stone particles, and this length, let's say LD, you can design based on your requirement. The deeper we go, the better, but then the discharge will increase because the length of flow path reduces. So there is an optimal one, maybe roughly half the downstream slope we come inside. And as you can see, if the flow line comes and meets the drain, there is going to be no erosion or piping because the particles are not being driven to outside world. Of course, you have to design the grain size properly so that the particles are not washed into the drain. Third one, which is rarely used but occasionally used, is called a chimney drain, wherein you make it vertical and of course connect it with blanket drain at the bottom. And in this case, the water is intercepted at a fairly high elevation. It doesn't go to the bottom at all. So these are the various alternatives of trying to depress the top phreatic line into the embankment. Now you can combine the confined and unconfined flow. That is, if you have an earth dam on a pervious stratum, what happens? You have together flow in the dam and through the foundation. Now this is also pervious. Now the flow would be, let's say I'm providing a toe drain, but you will also find flow lines coming here. Please remember, this being an equipotential line, they have to meet vertical. We also have problem of piping here. The reasons are twofold. One is soil particles may be washed away. Secondly, the gradient is upward. And we have studied this phenomenon of piping, or what they call sometimes as quicksand phenomena. The downward force due to gravity is opposed by the seepage force. And the downward is gamma submerged. That is the gravity, submerged unit weight of the soil if I take a small element. And upward is I gamma W, where I is the hydraulic gradient, and that multiplied by gamma W gives me. If this is equal to 0, the effective stress is 0, and then because there is nothing to hold the particles down, the particles try to move up, and that is how erosion will start, piping will continue, and the whole channel will form. Many times it comes back, and there are some dams which have failed because we didn't take care of the downstream side. And this I critical is given as G minus 1 by 1 plus C. We have derived this. is approximately equal to 0.9 to 1.1, and you have to check for the piping phenomena. So how do we do that? Again, if you draw the flow net here, let's look at what is happening near the toe. So what we'll have to find out is what is the head here and what is the head. So you know the head difference, and what is the length between the two, L. So I calculate the gradient for the element closest to the surface at the point of outflow is equal to delta H by whatever is the length. So that I is the gradient with which water is coming up, and what we have to do is this I critical by I should be greater than, usually with a factor of safety of 5. We make sure that the critical gradient is, actual gradient is a small fraction of the critical gradient, then you are sure there will be no piping mechanism or boiling or quicksand condition. The other way you can do this, prevent downstream toe failure, is to provide what you call as relief wells. What we do is we provide here relief. You make a hole and fill it with gravel so that this flow line will meet with the drain, and these are not, it's not a wall or continuous one. If I look at the longitudinal direction, I'll have these relief wells at a spacing of, let us say, maybe 3 to 5 meters. Otherwise, you can also provide a pitching. You pitch the downstream with heavy stone, which will not be washed away and also will prevent the particles being taken care of. So different methods of preventing piping would be to provide inside the embankment, toe drain, blanket drain, and through the foundation we again have pitching or relief wells. So we now looked at the different situations wherein you have embankment to store water. Suppose we don't have enough good material which will prevent flow through, then we have, instead of a homogeneous dam, use of only one material, we use what is called as a composite dam, or it's called zoned dam, where you have two different materials. You can have, this is called the shell. It can consist of coarse grained material, whereas this is called the core, which is consisting of fine grained material. Now you can say that the permeability of the shell is much higher than permeability of the core. K of the core is usually very, very low, 10 to the power of -7, 10 to the power of -8 centimeters per second. So it is relatively impervious, but you don't need a lot of material. You just need only a very small material compared to the overall volume of the dam. The shell consists of coarse grained material, which is definitely stronger. That means its friction angle, as we'll study later, is higher, is high, so that I can have steep slopes. If I have fine grained soil, I may have to use a 2.5:1, 2.5 horizontal, 1 vertical, whereas with this maybe I can even have 1.5 horizontal is to 1 vertical. I can make the dam smaller, steeper, with the core inside. But the problem now would be you have two different materials. That can happen even in the foundation. For example, I have within the foundation, I have layer 1 with permeability 1, layer 2, permeability K2. So when the flow is taking place and the flow line meets here, what will happen to the flow line in the second layer? Same thing can happen here too. You will find that when you have two different materials, what happens to the flow net? That's a very important practical aspect that you'll have to consider, because the permeabilities are not the same they keep varying from one point to the other. And if that happens, it is a layered profile, or you can say a non-homogeneous medium. What will happen to the flow path or flow net? It's a very simple modification. We'll again go back to your earlier concept of physics. When you have light traveling through two different materials, you know how it diffracts or gets refracted in the second medium. The same thing would happen here. Suppose I have a boundary between two layers, layer 1 and layer 2. The flow line, let's say 1 here, AB, meets with the interface. You have the soil on one side, which is layer 1, with a permeability of K1, and on the other side of the interface, let me call this as interface, the permeability is K2. So when the flow line meets the interface, what will happen to the flow path? Will it go straight or will it deviate? In all practical cases, you can even derive that it will not be the same, and the angle at which the flow line is meeting the normal, let's say is alpha 1, the angle at which the flow line goes into the second medium is alpha 2, will be different. Please remember, this line is orthogonal to the interface. So alpha 1 is the angle with respect to the normal in layer 1. Alpha 2 is again the angle the flow line makes in layer 2, whose permeability is K2. Similarly here, the flow line CD meets the interface at D, and then the flow line passes into the second medium, making an angle alpha 2 in the second medium. And you can derive easily from physics or even from fluid for continuity, tan alpha 1 by tan alpha 2 is equal to K1 by K2. The angle with which they meet and progress into the second layer are proportional to the coefficients of permeability. So how do I use this? This is exactly the same thing as what you would say. Imagine this is a ray of light. It is meeting a medium with a different coefficient, and then you will find that the ray will change through the second medium depending on its index, the transmission index, and the relation is exactly same as in physics. Tan alpha 1 by tan alpha 2 is equal to K1 by K2. Just to illustrate to you, let us say K2 is very high. This is something like a granular material, and let me say K2 is equal to 100 times K1. Then what will happen to alpha 2? Tan alpha 2 will be equal to tan alpha 1 into K2 by K1, and this we said is 100, so which means tan alpha 2 is close to infinity, and so alpha 2 will become pi by 2. So what it means is, the moment you provide a drainage layer, we talked of the earth dam, for example, earlier, here is the blanket, and the flow line will come. Once it meets here, it will simply go along the one, because this angle is 90 degrees to the surface. As you can see, you will have a 90 degree rotation. So that is why we provide a very high pervious material. What happens if the second material is a small one? If K2 is 0.1 times K1, that is, you are meeting with a very small one, in which case tan alpha 2 is equal to tan alpha 1 into 0.1. So this tends to be close to 0. So alpha 2 will be close to 0. So what it means is, when you provide the core, the zone dam, here is the composite or zoned at the dam, and here is the core. This flow line will come. If I draw, then instead of going, it will be perpendicular. Alpha is 0, so it will come along, and because this is highly impervious, K2 is very small compared to K1. The head losses will be very high. A impervious material will make sure the flow is lost, and then you will find that in this case there is no problem as far as the downstream slope is concerned. And that is the reason why we provide a core. A core will ensure that the flow is confined within the impervious zone, and by the time the top flow line comes out of the core, it will be fairly below, and there is no chance of the flow line hitting the downstream slope. So that is why we use zone dams. You have a casing or shell which consists of coarse material, and inside is a core with a low permeability material. So these are the ways in which you can handle a non-homogeneous medium. When you have 2 layers, you can make it 3 layers also. There is absolutely no problem. Layer 1, layer 2, and layer 3. All it means is that it comes something like this. It meets again, it will go in 3rd direction. So the flow line keeps changing its direction depending on the permeability. K1, K2, K3. Any number of layers you can handle without any problem, as long as you satisfy this criterion that tan alpha 1. So this is alpha 1, this is alpha 2, and this will be alpha 3. Tan alpha 1 by tan alpha 2 is equal to K1 by K2, and similarly tan alpha 2 by tan alpha 3 is equal to K2 by K3. So you can build flow nets even when you have a stratified deposit or a layered deposit, or you are providing a core. We also sometimes take this core into the ground. If I have a sand stratum, we make a pit inside the ground, fill it with clay. So here is you have a clay core as a cutoff. This is something like the sheet pile we were talking about, a diaphragm wall. At the dams we usually provide a clay core inside, and so you will have 2 different materials, and that will be easily handled in constructing the flow nets. One more aspect that I would like you to talk would be the uplift pressures. You have to worry about uplift pressures, particularly for concrete dams, barrages, weirs, etc. Let's say we have a dam which is storing water of 100 meters or something, and here is the downstream side. If I draw the flow net as you have drawn earlier, let's draw the equipotential line. 1 here, and if this is H, let us say how many head drops? 1, 2, 3, 4, 5, 6, 7, 8, 10. Can I say that the head will be 9H? This will be 0.8H. This is 0.7H, 0.6, 0.5, etc. On the bottom of the dam, can I say that the uplift pressure varies something like this? So the weight of the dam is here. This is what you can call uplift pressure. The water pressure is acting on the base of the dam, and you have to check for the stability, because let's say this is 100 meters. Then you will have 100 meters here, 90 meters of uplift, 80, etc. And you can see that if I take the centroid weight of the dam, for all I know, you may have a moment trying to push it up or lift it. If it is going to lift it, there is another problem. If you don't take care of it, there can be a lift, which means there is a gap here and water can enter. Then the dam becomes unsafe. So whenever you draw the flow net, on the bottom of the weir or the barrage, you have to calculate what are the uplift pressures. They may not be something like this. Probably when I go down a little bit and then provide a cutoff, etc., maybe instead of 100, I may have something less. So you have to design in such a way that the uplift pressures are also less. So please remember, you have to estimate based on equipotential lines. Any flow net if you give me or you draw, you can easily see that the upstream equipotential line is full head, but any other one will be less. So depending on the location of the equipotential line, I can easily calculate what will be the uplift pressure, and that will be the one that will be acting on the base of the dam or the weir or the barrage. And you have to make sure under the full reservoir condition, the weight is adequate, and now you realize why the shape of the weir is generally something like this. We have a very high thickness or large thickness here, so that if you have a very high uplift pressure, the centroid is very close to the left end and there is no chance of overturning. You have to make sure that weight of the barrage or the weir is always on the upstream side, so that the uplift will not make it topple. So this is how we can do that.